All right.
I see we're recording. Okay. Hi, everybody. My name's Elliot Garbus. This is a project review of creating a MIDI clock. And I'm going to be talking about multiprocessing, Python, and MIDI. First, a brief public service announcement. If you're not aware, PyCon 2020 was canceled. However, everything is now available online. All of the speakers have done presentations and have put things up online. So that's all available. I've seen a couple of them. They look quite good. All right, so I will introduce myself, talk specifically about the project goals, give a quick bit of background on MIDI clock in particular, talk about finding a high-resolution timer in Python, talk a little bit about the difference between threads and multiprocessing, specifically in Python, how MP is applied to this use case. Then I'll do a code walkthrough and then come back and summarize some of the key lessons learned. Please feel free to interrupt me at any time once I get going. So as Austin mentioned, I'm a retired high-tech executive. I worked at Intel almost 30 years. The last 12, I was a VP. I hadn't done any coding in a long time, but in retirement, started coding again. Primarily, I do whatever the hell I want, but occasionally I'm a management consultant and advisor. I'd been a Python hobbyist largely, creating programs to control music equipment on Windows and Mac that I've posted online and given away, and I really enjoyed that. Just recently, I had a manufacturer approach me about creating some software for them. So now I'm a professional. So not making a lot of money, but it's a hobby, so it's a great trade-off. Project overview. So musical devices can connect together across a standard interface called MIDI, which is the Musical Instrument Device Interface. This is a very simple serial protocol. There is a single byte message, which is a MIDI clock, and it enables you to synchronize multiple devices at the same time. So the requirement that I had to make this work was an accurate low jitter timing source. And when I say low jitter, I mean, I'm getting a steady metronome-like clock. I can't have a lot of swing between the beats. I'm going to just show a very brief video. I hope this works okay, that shows what happens. Whoops. So you see the lights are not flashing in synchronization. So that's sort of the problem statement. We've got the app up there. Okay, so you see the lights are flashing together, which is really what we're looking for. Okay, and then this is the user interface, a rather simple UI for the tempo. All right, so a little bit about MIDI clock and BPM. BPM stands for beats per minute. A set of traditional sort of music rates from 40 to 240 BPM are supported. You see 40 is very slow, and 200, or what usually ends up being 240, is very fast. The device I'm connecting actually has a BPM rate, looking at the lower table, that goes up to 6,000, which is really a very, very fast rate for BPM. And in fact, it doesn't actually sound like beats per minute anymore. Sounds kind of like an interesting ripping noise, but it's a special effect and it's supported by the hardware, so I wanted to be able to support it in the software. So the MIDI clock is just a message. It's the master clock. It sets the tempo of playback. That clock message gets sent out 24 times per quarter note. And so the message rate, so we've got some message rate is, I'm getting a message that I'm muted. Can you hear me? Okay. I'm now unmuted. You can hear me now?
Yeah, we're good. I was trying to mute someone else, and then the name switched around on the.
Oh,
good.
okay.
Carry on.
Oh, all good. Okay. So this clock timing message gets sent 24 times per quarter note. So, you know, if your beats per minute were 60, right, which is, you know, sort of slow, right, that would be 1 beat a second. And in that second, I would have to send out 24 messages. When I'm doing 6,000 beats per minute, I need to send out a message every 417 microseconds. So I need a more accurate time base. So turns out there's an awful lot of timers in Python. Now, the most natural timer for me to use would be the timer that's part of the UI kit. So I use a UI framework called Kivy. It has a clock in it, but the resolution is 15 milliseconds. It's synced to a 60 frame per second frame rate, and it's also very high jitter. So it's not at all appropriate. I started with that. Not only could I not go fast enough, the jitter was audible. So then there's time and time underscore nanoseconds and the perf counter and monotonic counters and process time. Now, just reading about it, it seemed that perf counter was the best fit. Highest available resolution to measure short duration, includes elapsed time during sleep, and is system-wide. And we'll come back to the notion of sleep, but that ended up being an important feature. In one of the PEPs, there is a discussion about clock resolution. I've got a link to it in the bottom of the slide there. Now, I'm just going to jump quickly to the code that looks at timer resolution. So this code is very simple. It runs for 1,000,000 times across each of these different clocks. And you can see, I hope this is legible enough. You can see that I'm collecting up the difference in 2 consecutive calls to time, then collecting all of the times that were not equal to 0 and taking the smallest one and printing them out. So if we go and run that, as they come through here, we see that the performance counter, the minimum time is 100 nanoseconds. The others are all substantially more than that. And so the perf counter ended up being the winner in this beauty contest and what I used to set my time base. Okay, so then I had a challenge that now I had a good time base, but because I'm running a GUI is an event-based system. It has got its own event loop. So if I put in kind of a spin weight based timer, which is what I need to do to get the accuracy, I'll basically hang the UI. It'll lock up because all the time will be spent in the timer, which is not great. So then I'm left making a decision between threading and multiprocessing. Threading in Python, threads run concurrently, but one at a time. So my timer thread is going to be competing for execution time with the event loop of kivy, the GUI. Threading has the benefit of a shared address space, meaning each thread covers the same address space. So you've got the same variables. You don't need to do anything to think about how you share data. You're in the same address space, you have the same variables. And then it's faster to create and delete threads versus creating and deleting processes. Now in multiprocessing, the processes run simultaneously. There's a separate address space, so you've got more complex data sharing, and they're slower to create and delete. In my use case, I create the timer process once and I delete it at exit. So that's not an issue. There's hardly any data sharing, as you'll see. And so it was very easy to pick multiprocessing. But most importantly, the threading was problematic because it resulted in jitter. So I didn't get that steady clock that I need for synchronization. And again, it's because the thread and the event loop for the GUI were competing for execution time. Okay, MP for this use case. I don't think you could come up with a simpler use case for multiprocessing than this program. And yet there was still a lot of interesting gotchas and learnings that came out of it. So there are two processes. There's the GUI process, that's the user interface element, and then there's the clock generation process. I've got two shared variables, one called shared BPM and the other one called run code. These communicate from the GUI to the clock generator. So the clock generator doesn't need to send anything back to the GUI. So I don't have to be concerned about locking or synchronization or mutex or semaphores or anything really significant. So this ended up being rather simple. Now what's fascinating is the way multiprocessing works the way I'm using it, is you create two processes. Each process gets its own Python interpreter. It also gets its own copy of the program I'm running, which I've just called main.py here, but it includes everything. And the way you distinguish between what you want to have run is through dunder name. Now, I'm sure all of you are familiar with using dunder name at the bottom of a script, that if it's equal to main, that's the thing that you're running. What took me by surprise is that dunder name in the other process has a different name. It's MP main. And because you've got the same code in both processes, you basically are hiding code behind an if name equals dunder name to ensure which code is running in which process. Did that make sense to anybody? I'll take your silence as yes, we're with you. Okay, I've heard that some folks like the beer and the food that usually comes with this meeting almost as much as the meeting itself. So here's my virtual pint of beer for you. Less interesting, let's jump into the code. So this is all of the code in this program. It's relatively short. It's about 200 lines of code. That includes both the UI and the multiprocessing piece. I'm going to focus my discussion on the multiprocessing piece. If you do go into the GitHub repository, you'll see there's a few directories. There's one called dev tests. This was some simple tests that I had developed during development. This includes that timer test, timer resolution. All the images that are in the GUI are in this images directory. there's a MIDI clock dist directory. And in there are 2 spec files for PyInstaller, mac.spec and w10.spec. Those, if given a PyInstaller, will create a Macintosh or a Mac OS executable, or on a Windows system, a Windows 10 executable using PyInstaller. Config startup is some configuration code just for kivy, the GUI, and largely what it's doing is making sure the window opens up in the last place it was located. And then, as I mentioned, most of the code is in main.py. There's a MIDI clock.kv, which is how the GUI is structured. And then there's a README. Okay, so first let's just bring up the app and show it to you. This is the same thing you saw on the video. I select a MIDI output, and then I can select the tempo. So let's jump into the code. So most of the action is in this MIDI clock gen, but before we go there, I want to go in and examine this dunder name piece. So all of this code looks rather the way you'd expect it to. And then in the middle of my program, I've got if name equals dunder main. So this code that's here, which includes all of the initialization for the GUI and all of the code that is particular to the GUI and starting up and running, is protected by if dunder main. This code exists on kind of both sides of that diagram. So let's take a look. So I've got my MIDI clock generator. I have some shared variables. And in the multiprocessing module or library, value is used to indicate a shared variable. That is, it's shared across both processes. I indicates that it's an integer. 60 is the initial value. The run code is used to stop the process, the clock process, from the main process. If you don't stop it, you'll be left with this rogue process running on your machine. So looking at how this gets invoked, and then I'll jump back. There is a method called onStart. And onStart, I get the MIDI ports, and set up my window. And jump back up here. Sorry for the scrolling. Hope you don't get dizzy. Okay. If we look at the MIDI clock generator, this is where most of the time, well, most of the time, all the time in the program is spent here. So this MIDI clock generator gets the output port, that's the name of the MIDI port, the shared variable BPM, and the shared variable run. Now, when you want to read the content of those shared variables, which again are elements of this class value, you have to say bpm.value. I had a number of bugs where I failed to do that. So just something to keep in mind. So I open up the MIDI port. I create a MIDI message, which is clock, which is the single byte message, which is part of sending a MIDI clock stream. And I call that a clock tick. So while run dot value, right? And again, run is a shared variable. So to get its content, it's dot value. While run dot value is not 0, I calculate the pulse rate. I've got the BPM value here in the inner loop. So by changing that variable, I'm actually changing the clock rate. So it's highly interactive. I send out the tick.
Hey, Elliot,
Yeah.
can you hold on a second? Is anyone else having a hard time hearing Elliot, or is it just me?
Yeah, his mic is cutting in and out.
Yeah.
All right. I'll lean in a little closer.
Yeah, I'm not sure what it is.
Can you hear me clearly now?
Well, it's like, I'm not sure.
It's more like it keeps shorting out almost, but it doesn't go all the way. You know?
Yeah, it's weird. I don't imagine you're like leaning on a microphone or anything. It got particularly bad in the last couple of minutes.
All right. Well, shall we keep going and see if I'll try to speak up and closer to my mic?
Maybe if you mute your or disable your video there, maybe that would help.
Oh, okay. That sounds like a good idea.
But if then we don't hear anything from you, then we're just gonna not realize you're speaking.
Can you hear me?
That sounds pretty good.
All right, that could be part of it.
Well,
I would close and reopen Zoom.
Okay.
yeah,
For me?
yeah. I guess that might be the case.
All right, I'm gonna stop
Like
sharing.
reinitialize the mic.
What's that?
Kind of like reinitializing the mic. Like
Yeah.
close
All
Zoom
right.
and
So
reopen.
I'm going to drop and come back.
Okay. It's like we needed a better MIDI timer.
Yeah. Yeah, that is kind of a funny thing.
A little coincidental. Going through the tunnel. Yeah. Hey, yeah. Good comments.
I feel like Metachlorian would be a great name for a MIDI library.
MIDI Chlorian. Good call. Hopefully he's able to rejoin.
Yeah.
Reinstall the OS. No, Richard.
Oh, you never worked help desk, man. That's a great time waster.
Yeah, sure. I guess we're recording desk videos here, so I'll sacrifice my visage.
Now unmute. Can you hear me now?
Yeah.
Yes.
Yeah.
Better? The same?
Much better.
Much better.
Sounds better. Go ahead and try and share your screen again, Elliot.
All right. Let's see what happens. And we were.
Yeah.
All right. All right. Can you hear me now?
Yep.
All right. Here we go. So the BPM value is right in this inner loop. I send the clock tick. I read the time. And if my BPM value is less than or equal to 3,000, I go to sleep for 80% of that period. And the reason I added sleep in was that I saw this app consumes an awful lot of power because it's just in this spin loop, although it's doing very little. By putting the sleep in, the power levels dropped dramatically.
Nice.
So that was the reason for that. And then I just sit and spin, reading the performance counter until the pulse rate is consumed. And so this process, once it's kicked off, it just runs until the run variable is set to false or 0. That kind of breaks this while loop. That process gets started by a method launch process. So I pass in the output port. If the process is already running, I close it to create before I create a new one. I kick off the flashing LED, and then I set my run code value to 1. Again, that's that shared variable. And then I make this call to process, which has that MIDI clock generator as the target. It's got the arguments, and then it can get a name so that on the task manager, I can actually see the process show up. And then I call process start, and that kicks off that process. When I want to close the process, I use the end process method. I set that value, the run code value, to 0 so that the other process terminates. I run a join, which says I'm going to wait here until that other process is finished, and we bring the two processes together in one, and then I close the process. Again, if you don't do this, if you don't close the process, you'll have a rogue process running in your machine for a long time. When I was first starting, I had quite a few of those running around and consuming a lot of power. So some lessons learned. All right, now jumping into the main part. So for Windows, if you want to use PyInstaller, you need to add freeze support. PyInstaller, if you're not familiar with it, lets you create a standalone executable. There's a set of imports here that are all focused on how the GUI works. And then there's a set start method. This set start method doesn't do anything for Windows. Windows, you always spawn. And it's required for Mac prior to Python 3.8. On Unix systems, you can spawn or fork. Because Windows only spawns, I set the Mac to spawn as well. These are some, again, functions related to the UI. And so let's see, I wanted to show, okay, so first at startup, right, I create the MIDI clock generator class. That's the class that we saw above. Then on let's see. Thought it would be on start. I'm not, for some reason, I'm not seeing it. And then I obviously never call it, so it doesn't run.
On start was down there a little bit. You're looking for a method name?
On start, but I didn't see the MCG. So there's on stop. Well, that's embarrassing. Obviously, somewhere it's being kicked off. Oh, it's probably just here. This is sufficient to kick it off. Let's go back to, yeah, that's all it takes, right? That kicks it off. And then launch process has got to be called from somewhere. Oh, I'm sorry, it's called from kivy. There's an event that's created in the UI that makes the call to launch process. So that when a when a MIDI port is selected, app, because it's declared at the app level, MCG is the MIDI clock generator. It calls launch process with the text that's on the button. So that's how things get kicked off. Then, when we stop, when we do the close, oops. On stop gets called when you hit the close button on the app, and that makes the call to end the process. This configuration writes basically the position of the window so that the window always appears in the same spot. So that is that's the code. Any questions on the code before I jump back to the presentation? Dazzled or asleep? Okay.
I'm actually curious about the physical MIDI interface. So how do you connect to the devices? Is it that like 7-pin connector or?
So MIDI is a 5-pin DIN connector, and so there are USB to MIDI connectors, but MIDI has evolved, so now there are transports directly on USB and on Bluetooth. But in these systems, I've got a little adapter that goes from USB to a 5-pin DIN connector. And there are 2 connectors, one for out and one for in. In this app, because I'm only sending messages, I only open an output port. I'm not listening to messages. So there's no input port.
Cool, thanks.
You bet. All right, so let's see. Jumping back to some lessons learned. All right, in summary, I successfully used multiprocessing to create an accurate low jitter MIDI clock. Lessons learned, using the dunder name to control code in separate processes and what goes into each process. The documentation is a little bit sketchy. They make references to this being important, but until you see it, it doesn't really make a whole lot of sense. And in fact, why don't I just go back to the code for a minute. You'll notice here, I've got a print statement to print out the name for that process. And so let's just run it. So now when I connect to a MIDI device, we see that name is dunder MP underscore main, which is not something I'd ever seen before.
Now, if you had more than one, spawn more than one process, what name would it have used? Would they both use the same MP name, or?
I suspect so, but I don't know, and I didn't see anything in the documentation.
Or maybe when you spawn the process, you can control what that ends up being. Maybe that's it. I don't know.
No, you can give the process a name, and I gave the process a name, MIDI background, and that name shows up on the process manager, task manager in Windows.
Sure, sure.
Right. But that dunder name, I suspect it's probably just dunder MP main, independent of the number of processes. But I haven't tested it.
Yeah, that would prevent you from running different code for differently spawned processes, though. So, yeah, interesting. Okay, no, that's cool, though. Thank you.
Let's see. Well, you would associate the code with the process here. I think the big thing is really just separating out main. There are a lot of techniques within the multiprocessing library for managing like a pool of processes, which
Okay.
if you were doing something compute heavy would be, the way you'd go about it,
Okay.
right? You'd
Sure.
say, hey, I'm going to create a pool of 5 or 10 processes, and I'm going to, deal work out to all of them, or deal work out to them as they finish. But
Okay.
this, in some ways, this is almost like a rudimentary example.
Sure.
It happened to be, it was a perfect fit to the workload.
Yeah.
So I've used pool quite a lot, and I usually have just one instruction set. What's interesting here is that you have completely different instructions being run for the different cores.
Yeah. No, thank you. Yeah. All right. So, resuming. The next thing is that multiprocessing.value was used to create shared variables. And again, there's a whole lot of resources for different shared memory mechanisms. For communications, there were pipes and queues. But again, this rather trivial use case, value was a very easy way to control the app. I think, as you saw, the element that bit me more than once was needing to refer to those instances as sort of name.value to get access to the underlying variable. It was interesting to see the very wide range of attributes associated with all of the timers in Python. And again, that link back on the previous page had very similar code and very similar test results. And then sleep was a very effective power optimization. Now, I used it as 80% of the period when the clock rate was below 3,000, and I got to that value experimentally. There's also a lot of jitter in the sleep time. It has the same attributes as time. So limiting the amount of time you slept and then putting the kind of the spin loop at the bottom after you woke up was an effective way to balance the sleeping and the execution, again, with the goal of optimizing power. And that wraps things up. Any final questions?
Yeah, I had a question. This is Dave. Can you hear me?
I can hear you loud and clear.
Oh, okay. This is Dave Henderson. How did you measure the jitter? Did you use a scope or analyzer or any other MIDI equipment to see that your jitter was minimal when you were done and the timing was accurate?
Yeah,
How did you figure that out?
There were two things I did. One was I just printed out times. So I was capturing timestamps of when I was sending the messages. So during the development, I was capturing some of those timestamps and just printing them out from the inner loop. In fact, I think I had put them in a list and then saved up like 1 million of them and then just did some analysis on them. So I wouldn't have the print time in my inner loop. And the bigger thing was really just my ear. Like all of the other methods I tried, it was really obvious that something was wrong. With this method, it was just everything was rock solid. So both a little, throwing up a list of values and then doing a little analysis, but more importantly to me was just that it was right to my ear.
So you used Kivy on both. Did you have any differences? Maybe I didn't pay attention, but as far as the Mac and the Windows version, what sort of differences did you have in the Python code besides the packaging?
There's oops, let me go back to there was just a couple of things that were required for the Mac, or really just one thing, and that is this set start method to spawn. So wheels are not available yet for kivy on Python 3.8. So I'm still using Python 3.7. And so I needed to set the start method to spawn. The default method on the Mac prior to 3.8 was fork.
Fork, okay. You explained that already, okay.
Yeah, so setting it to spawn made it the same as Windows. And then,
Okay.
then of course, right, the files for the PyInstaller are different. There are some differences there. And then the other thing, which is not a difference, but something that just needs to be done when you're dealing with systems that have multiple resolution, is when I've got images or sizes, I have to list them in a pixel independent way. And so Kivy has two mechanisms for doing this. One is DP, which is sort of density independent pixel. And the other one is SP, which is for fonts. But when you say 10dp, then an internal DPI measure is used to adjust this value. And the Mac has twice the pixel density of the PC. Even though I've got a 4K screen, the way Windows handles it, it's half the pixel density. And so using these kind of DP mechanisms, and you can either have it in a string or have it more like a function call in this padding here, allows you to have exactly the same code across systems of different resolution. And that was another thing. It's the same on both, but it's mandated because I'm working across systems with different resolution.
Cool, thank you.
You bet. Oh, and here you can see the font size. Again, is at 20 SP. And the difference between DP and SP, they're largely the same. But if you had some adjustment on the font size, like large fonts or small fonts, that would go into what adjusts the number 20 here. So you would get some sort of accommodation based on your system set.
Elliot, I've got a question when it's my time.
Okay, go ahead.
What I learned from going to some talks by people designing autopilots is they had to run real-time operating systems, because if you're counting on a tick from a sensor or an actuator, things can get unstable pretty quickly if the operating system decides to do some house cleaning and delays certain of your operations. So what I'm wondering is if you looked at how your jitter might depend on what else you're doing with your operating system in that moment in time.
I haven't looked at it. You know, my use case when I'm running this, I'm not running anything else. I've got multi-core systems, and you know, maybe I've just been lucky. It's also, I'm sending a clock message out at 6,000 BPM, which I don't often use. That's 400 microseconds, which for a microprocessor is a good long time. And more importantly, across times that would be more typical. Typically, you'd probably have 100, 120 BPM. So, you'd probably be like 25 milliseconds. That's a long time compared to what an automotive sensor would need to capture. So I very well may have just been lucky because I've got a lightly loaded system and this is all it's running. And then the timing accuracy is not that hard. And then perhaps more importantly, if there is a little jitter, something may sound off for a beat or two, I'm not going to drive into a brick wall.
Yeah. Thank you.
Yeah, you bet.
So Elliot, I've got a question and then some experiences, I suppose, to share. I'm curious about what was the variable? Can you go back to showing how you passed variables between the processes?
So, let me bring this down. So these are the two shared variables, the shared BPM and the run code. And these are both instantiations of the value class. And then they get passed in as arguments to the process down towards the bottom of the screen.
Okay, and then you just reference them as normal on the other side?
So I reference them here, and then right on the other side, I reference them the same way. So the run code is only referenced inside this class, and when I call end process, that run code value gets set to 0, right? Again, kind of closing out the process. And then the BPM is tied to that slider. So I imagine if I look in here, and here's the slider. So on value, which is when the slider value changes, I'm setting that shared BPM.value to the integer value of the slider. So the slider moves and the value gets set on that variable. So very straightforward.
Yeah, that is. It's been a while since I did my multi-process project. I think I ended up using named pipes, which I found were fairly complex and a little bit unreliable. And probably the biggest hassle was I had to develop a whole messaging protocol to send and receive data. It was nowhere near as easy as sharing member variables like that.
Yeah, I think it really goes to the simplicity of this application that, those messages are one way and very simple. So it really lent itself to using this. A named pipe or a queue seems really like overkill for these, very, very simple use cases.
Yeah, I would agree. Your commentary around Spawn reminded me of an experience I had. I did not play with Spawn. I played with forking. And something unexpected I discovered is that anything that it's either memory values, I think it was variables that you created and assigned values to when you did a spawn, basically the current I'm sorry, not spawn. If you do a fork, the current process essentially gets replicated with all of its memory state. So I had some weird circumstances I wasn't expecting where I would fork to a new process, and it was essentially running code that I had started in the first one, and I wasn't expecting that. So Spawn's probably a better tool to use for doing that because you're going to start, it seems, with more of a virgin installation as opposed to cloning something that's already running.
Yeah, I think it's very much a function of what's the class of problem you're doing. I think the benefit of fork is that it's really a child of the kind of your master process.
Yep.
So you don't have to be so concerned about shutting down processes. But as you found out, you've got all of the challenges of like where are these variables? And file handles in particular can also be quite tricky. because they get shared as
Yeah, I wasn't even aware of Spawn. I guess just the examples I had found, Fork, it worked well enough that that's what I ran with, and never went back and explored spawning. So I ended up architecting my app so that it would always launch or fork all the additional processes right off the bat before I started doing any other work because of that behavior.
Right.
So lesson learned.
Yep. Well, there you go. Well, thanks for sharing.
I wanted to hit you up with one more thing. Sleep. You mentioned there's a lot of jitter in sleep, and as I mentioned in the meetup commentary, I've got an application that also does some pretty tight timing. I've got it down to, I don't know, 10 or 7 microseconds or so, much more granular than I really needed to. And initially, I had hoped that I could just feed in a nice high precision value to sleep and have it pop back out the other side and be accurate. And I discovered that it wasn't. It has a lot of jitter. If you feed in a large value, it has more jitter. But what I discovered is if I did a multiple step or a multiple nesting of my sleeps, I could get down to pretty fine resolution. So essentially what I would do is look at the time that I needed to sleep, and if it was more than a second, I'd tell it to sleep for a second. And then if it was more than 1/10 of a second, I'd tell it to sleep for 1/10 of a second, and just keep looping. And I think I've got 3 nests in there. The last one's like a 10,000th, maybe 100,000th of a second. And in doing that, it sleeps most of the time, but I still achieve the resolution that I was hoping for using the sleep function.
Well, that's
So
fascinating.
Yeah, it's a very low CPU way of solving the problem, but it does require you to do like a nesting. And I'm happy to share a code snippet. I was going to take a picture of it, but technical complications.
Yeah, no, I understand that. If the power consumption of this was really a concern, it'd be something I'd do some more experiments on. But this is kind of like, you know, in the can for me. But
yeah, no critique there. In my application, I had to have, I don't know, probably 100 threads running, maybe more. And most of the time they needed to sleep. The reason for the architecture was so that it would be simple to schedule. But the trade-off is I had to be in sleep most of the time. If I was doing a spin loop, I could do that across 100 threads.
Yeah, sure. Yeah, that's interesting. I may do some experiments there. If you can, yeah, shoot me a little code snippet, maybe I'll play with it.
Yeah, I'll fire back a comment with the code snippet in it, and folks can explore.
All right, awesome. Thanks. All right. Any additional questions, comments? Praise?
Elliot, you've learned a lot.
Thank you, Tom.
No, it's very interesting, Elliot. Is anyone else have any questions or thoughts or concerns, or
I got more.
Anyone have a complete presentation prepared as a surprise for me? No? Okay. You know, someday. No, actually, that was really great, Elliot.
Thank you. I'm glad you enjoyed it.
High-level application question for you. So you're sending out a beat to synchronize all these instruments. What else are the instruments doing? They must be getting feeds from somewhere you're trying to synchronize their activity.
I'm turning my video off because you were really breaking up, at least for me, when my video was on. I think the question was, so what else are these things doing when they're getting synchronized? Is that the question? Okay, so the 2 devices that you saw in the video both have delays or echoes as part of what they generate. And they also have modulation. So that is like a tremolo is an example of modulation, right? Kind of a musical change in the volume. And so you can synchronize those things together so that when you run audio through it, things gel and make sense, so that you can do interesting delay effects when you've got 2 delays that are synchronized to one another. So you can have them relative to the beat instead of just kind of seemingly at random. That the modulation, again, a tremolo is example, which is a continuous change in volume, that that is also synchronized to the beat and perhaps to your, to your echoes, to your delay. So that's what you use this kind of synchronization for. Other devices can play sequences. I wasn't doing that in this example, although I do have devices that do that. And if you've got a device that plays a sequence of notes, then it'll play those notes back at the rate of the MIDI clock. And there are a couple of additional MIDI messages for controlling sequences, and you've got a stop and a start. So you can have the clock going and then send a start message, and you'll hear like a drum machine might be an example. You'll hear the drum machine play at the rate that I'm sending out, and then I could send a stop message and the drum machine would stop, send a start message, it would start again. That makes sense?
Yeah, that makes more sense. I was envisioning like a keyboard or something. It was my picture of MIDI, which of course is very narrow. So that makes a lot more sense. Thanks.
Yeah, so using a keyboard as an example, right, you might have an arpeggiator where you hold a chord down and it plays the notes, in ascending and descending order. And that could be controlled by MIDI clock, and usually would be. And,
cool, thanks.
And often all of these kinds of equipment typically have got an internal clock and then an option to use an external clock. And it's when you connect multiple devices together, you typically want to move to an external clock. If I think about a synchronized delay, the Edge from U2 used a lot of dotted eighth note delay that was synchronized to the beat. So that's a good example of kind of a synchronized delay.
Makes sense. Thank you.
You bet.
All right. Does anyone else have any further questions or thoughts? No?
All right,
Okay.
everybody. Stay healthy and have a wonderful hot week.
Thanks so much, Elliot.
All right. Take care.
Yeah, thanks, Elliot.
My pleasure.
Thanks, Elliot.
Yeah, bye.
See you, everybody.